This is Random Clock Talk tape number 15 by J.M. Huckabee. Huckabee resides on the J.B. Ranch just on the north outskirts of Austin, Texas. Today's date is August the 27th, 1988. The subject matter that we'll be discussing today is edge tools used in lathe work. The discussion that I want to give today is related to clockmaking. That is, the size and materials that are ordinarily used in clocks, in moderate-sized clocks. We're looking here at some samples of the cuttings from edge tools in lathe work. Now let's take a look at these samples and see what we have and how that these cuts were made. Let's look at this sample right here. This sample is hardly visible by the TV camera. I'm working here with the lens of the camera at about 7 inches from this group of cuttings, and possibly we can get an eye loop on one of these little ones and look at it. If we can see that this is a continuous spiral, these cuttings are spirals as they come from the TwoBit in the lathe. Now, to give a judgment value on this, I would judge that this cutting right here probably represented removing about 1/1000th of an inch of material from the stock as the cut was made. I believe that this one right here probably represented no more than 1/2 of a 1,000th of an inch as it was removed. It's difficult to judge these dimensions because in the cut we have to understand whether or not the this swarf was coming from the surface, or whether it's coming from an edge. That is, we don't know the thickness and the breadth of the particular cut. But those are judgment factors of what I would think that the dimensions of these cuts are. This piece here probably represents 2 or 3/1000ths of an inch. Probably the latter, probably more nearly 3/1000ths of an inch removal from the stock as that one was made. If we look at these, I believe that one's bronze, this one is steel, I think that one is steel, this one is bronze. Now, as we step up a little larger to see what these cuttings are really like, let's take a look at this one. This is aluminum, and this was not cut on the watchmakers or clockmakers lathe. This was cut with a small engine lathe. That was a rather rapid cut from a piece of aluminum bar stock, and this probably represents, it looks like the cutting was coming off of probably a facing operation, and was probably removing about 10/1000ths of an inch with a fairly broad cut. This cutting here is, let's see if we can roll this apart and look at it. It looks like it is breaking up on me, but this cut is rather broad but thin, probably 5, 6, 7, 8/1000ths of an inch thick, and that was from a low carbon steel bar stock. If we look at this piece here, I don't know if the camera will render this in its proper color or not, but this is a deep, deep blue. That's the color blue that we would like to blue clock hands and screws and and whatnot. That's a beautiful blue color. Now, producing that blue color, you can understand the temperature that how hot this piece was as it was coming from the lathe tool. Now, what does this represent? This cut was made with a tungsten carbide tool bit, and the cut was from a small engine lathe, and in that particular lathe, this cut probably come off at the rate of about 1 foot every 5 seconds. So that's quite a rapid removal of material. This was cut dry. It was coming off very hot. Consequently, it is blue. Now, tungsten carbide tool bits, commonly called in the watchmaker, clockmaker trade as Carbide Tools, those bits can stand tremendous heat, provided that they're well affixed in their parent holder. Usually carbide bits are a small chip of material that is either clamped in place or cemented in place, cemented being brazed, cemented in place, and the temperature of this, it wouldn't take too many minutes of this to melt the brazing in the holder and release the cutter, the cutting edge, the carbide edge. Cuts like this can only be made for short periods of time with ordinary carbide tools. When this rate of material removal is being done, it is well to run a coolant, probably something like a half gallon of coolant per minute on the tool bit would keep the bit and the material cool and improve the finish of the cut as well as the speed at which material could be removed. Coolant is usually water with possibly 5 or 10% of emulsified oil added. The water being the primary coolant, the small amount of oil being a lubricant. This cut here appears that it was coming from the stock quite hot. It has a spongy look, which indicates that it was quite hot, and regardless of the tool bit, at that heat, very soon we would be out of business. The reason there is that the parent metal would begin to gall onto the tool bit, and as it would become plastic with the heat, then a smooth cut could not be effective. This was cut with a small amount of oil lubricant. I picked these up under the engine lathe out in the shop here this morning, and this one was quite greasy, and that indicates that it was coming off the lathe, that there was some degree of oil that was being used on the tool bit, and no real coolant. The purpose in showing these larger pieces is so that we can see in our camera what chips look like. Now this is a rather rapid cut right off of the Clockmakers Lathe. The Clockmakers Lathe is really a watchmaker's lathe that is fitted with collets for a little larger stock, and this is the type of cut that can be made on a watchmaker's lathe with suitable tools and suitable motive power. And this is one of the smaller cuts, and so on. Now, there is really no difference in the circumstances from the large ones here down to the tiniest ones, except degree of size. Everything, all circumstances are approximately equal except the degree of size. Now, we will be talking about primarily the Clockmakers Lathe, the Watchmakers Lathe, and the edge tools, and how that we make the cuts in various materials. Now that we've seen the larger pieces, let's talk about this a little further. In the machine tool industry, the power used is very great. The coolant that is pumped onto the work is very large in quantity. It's not unusual to pump 5 or 10 gallons a minute of coolant on a large tool bit in a large engine lathe. A gallon or 2 gallons a minute may be used on a smaller engine lathe, and that is dictated by the economics of production. It is how long the tool bit lasts, what time is required in the setup, how much productivity that we can get per hour. As the clockmaker, we ordinarily do not pump a coolant on the material that we're cutting. It is discreet to use lubricant, oftentimes some coolants, and the lubricants used can be some are better than others. Of course, black cutting oil is one of the finest lubricants. It's stinky, it has a sulfur smell, it's messy. You can use just a little bit of kerosene applied with an artist's brush. I oftentimes spray from the little tubular nozzle on a can of WD-40, as this serves as a coolant and a lubricant also. Of course, that fogs into the shop and presents another set of problems. Now, the question is, should our cuttings look like the samples here? Do we want our cuttings to look like these that I have exhibited here? The answer is generally no. Generally speaking, the answer is no. Of the AWI correspondence course students that I work with in the lathe work, I usually tell them, send me some samples of their cuttings. I usually return some samples that looks about like this. This comes from the old adage that the skill of a workman is known by the chips that he makes, whether that be a carpenter and the sawdust and the planer shavings and whatnot, or whether it is the lathe operator, the milling operator, or whatever it is. The chips indicate what our degree of skill in cutting and the rate and the finish that we will have. It is not proper, well, proper is not the word, it is not best to cut long spiral pieces like this. If we are dealing in larger work and you're bringing off spirals like this, which may get to being 10, 15, 20 or more feet long, you have a serious problem in disposing of the waste. As a matter of fact, in very large machining, oftentimes in a long cut, where the cut may run for hours on the lathe, the operator may sit with a small bolt cutter and hack the shavings by the hour. That's so that they can be stored into baskets and carried out in the waste. It is always best, it's best in our tool bits and our edge tools to grind a bit which does not produce a spiral cut like this, but that has a chip breaker on it, so that this is broke up as in the process of cutting. Then the chips can be brushed out, scooped out, in larger industry, actually carried out by the shovel and wheelbarrow loads. So, for the most part, these are demonstrations of sizes of cuts, and we'll talk about how we produce these, but in actual practice, we would want a chip breaker on the tool, so this is broken up so that it is easier to handle. Let's set the tools aside, or the chips aside, and think about what tools look like. For the clockmaker or watchmaker, we commonly use what is called gravers. A graver is nothing more than a piece of steel or whatever, the requirement being that it is harder than the work that we're going to machine. It's in some suitable handle, and the shape of it fits the individual's fancy. I'm sure that the person that made or originally owned this graver was very proud of it because it's ornately made, but I can assure you that all of this ornate material here does not produce results out on the business end. I obtained that one somewhere in an antique market, and I thought that it was unusual. It's the only one I own that looks that ornate. Most of the tools, the gravers that I own, look like this, or like this. And let's see what we have here. This is a piece of dowel, wood dowel from the hardware store, neck down a little bit. That's the end of a large pistol cartridge case, hole drilled in it. And the cutting bit here is a piece of high carbon steel. It's 93 thousandths of an inch square. I picked up several pieces of that square rod somewhere many years ago. They were about 3 feet long. I cut these into about 3-inch lengths, fitted them in the handles, and this material is just about as hard as you can reasonably cut with a file. After this, the tip was roughed out on a grinding wheel. Then this was heated bright cherry red, and about the last quarter of an inch, eighth of an inch, about this much on the end, and quenched in cold water. It was left that hard. The tip end of this bit cannot be cut with an ordinary file. Now, that gives me the strength of the toughness back here and the hardness right on the tip end. I've used these things for a long, long time, and I don't ever recall breaking but one. I broke one about 1/8 of an inch on the end one time. I let this run under a fairly heavy piece of stock and popped the end off of it. It is not unusual to shell just a tiny cutting edge off, to chip just a tiny cutting edge. These have to be sharpened frequently. You usually use these kind of tools by the handful, and when you sharpen them, you sharpen a group of them so that you don't have to stop in the midst of some piece of work. Now, these tools that I have here are suitable for use with the watchmaker's lathe. I notice, and they seem to be touted as such in some of the technical catalogs from the material houses. Buy yourself a carbide graver and you never have to sharpen it, and it lasts forever. Or that seems, it may not be so stated, but that is implied. Let me tell you up front, a carbide tool bit is not the universal tool bit for everything that comes along. Carbide has the characteristic of concrete. It can stand tremendous pressure, but it cannot tolerate being flexed. If you've never used a carbide tool, the first time that you use one, I will assure you that you will break the tip off of it within 3 minutes after you start using it. The techniques of using carbide is entirely different from tool steel bits. Let's look at this bit right here. This is a tungsten carbide bit. That's about 3/16 of an inch square. I use that in the slide rest on the watchmaker's lathe. That is very, very hard. Take a look at the end of this thing. It looks just about like just a blunt piece of metal. This is ground with ever so slight radius on the end, small amount of relief, and it is cut almost straight into the work and straight down. If you ever let the force go in this angle on the end of the bit, it'll shell the corner off instantly. The force must always be down. That did not start out as a lathe tool bit. That is a punch from a punch press and a stamping die. It is solid carbide. I picked it up in the scrap somewhere in a scrap die, and this is ground with a wheel that is called a green wheel. A green wheel. These can be bought through Sears Roebuck catalog and most any tool supply house. The green wheel is a very, very soft wheel. As a matter of fact, you can dress it with the end of a nail without hardly grinding any of the tip off of the nail. It is an open grit, and I believe the name of it is crystallite. I'm not sure. But the green wheel has one use and one use only. And that is to grind a carbide tool bit. And the green wheel, you feed this very, very slow, very easy into it. It grinds it rather rapidly, and you finish up it leaves it a bit rough, but you finish that up on a diamond lap. All right, let's look at another type of tool bit. Here is one that's 3/16 inch square. It's high-speed steel, and it is one that has great utility in the clockmaking trade. We'll pick several of these and take a look and see what we have here. And these are 3/16 of an inch square. They're about 2.5 inches long, ground on all four surfaces, and this is the way they're bought. This bit probably cost in a machine tool supply house about, or if you buy just one of them, it's probably $4 or $5. And if you buy half a dozen or so, they're probably in the order of about $3 each. The pure economics of this situation is that you grind a tool, grind a functional surface on each end of it, so you get twice the distance for your money. This bit here, same thing, except it's a little smaller. This one is 1/8 inch square, and you can see that it has a functional surface ground on both ends. This is 3/16. This is a piece of the 093 square rod. This is the bar stock. This is the same material that is used in the handle here. I use this in a tool holder on the lathe. Now those are types of tools that we may be using. Now let's discuss the cutting process. Let's discuss the cutting process. To begin with, let's just take the wrench pocket knife here and imagine that we are going to well, let's just sharpen this wooden peg. Try a different one here. Let's say that we're going to sharpen this wooden peg as we would a pencil. Now, in the sharpening process, we do not cut like this. We do not cut like this because that just will not cut. Think about slicing a loaf of bread. Think about slicing a roast. We cannot cut straight into the material, but we make a slice. We make a slice. If we were sharpening the pencil, we would make a slice, something like this. The same is true in machining metals. We need to make a slicing cut. If we make a straight cut like this, almost immediately the material will begin to gall onto the edge of the blade. It obscures the cutting edge and cutting ceases. If the cut is made in a slicing operation, like this, if that cut is made in a slicing form, then the cutting edge becomes, to a degree, self-cleaning. The cut becomes very smooth, and the energy required is considerably less. One of King Solomon's statements in the biblical scriptures, in his statements of wisdom and counsel to young men, said something like this: if the tool be blunt and you do not whet the edge, you must put forth greater work. Now, King Solomon realized that in his wisdom before the modern day engine lathe was ever imagined a possibility. And that is exactly the thing that we must have in our machining operation. The tool must be sharp. The tool must be sharp. There is no substitute. There is no escape. In order for me to make a cut as small as this, which may be in the order of 1/1000th of an inch or 1/2,000th of an inch cut, the edge on that tool must be no more than about 20% as broad as the cut that we're taking. That says that the tool, to make that cut, must be razor sharp. The tool to make this cut does not have to be that sharp, but it requires a lot more energy and a lot more heat is produced. Heat is the enemy of the cutting edge. And the localized heat on the cutting edge is greater than we would ever really imagine. Take, for example, if we go to catch a center in the end of a small pivot that we're going to drill, a small arbor that we're going to drill to replace a pivot in, we would be working on the very tipmost part of that tool bit. The very tipmost part of that tool bit, we must be very, very gentle, because the pressure in pounds per square inch is tremendous and the heat in the area is great. It is, though the quantity of heat, the total quantity is not great, in the concentrated area it is. And we can lose the tip of that tool bit on a hard arbor in 1 second. That's how fragile and also how important that cutting edge is. Now that we know that we want a slicing operation to keep the cutting edge clean and functional, what do we want the cutting edge to look like? Look at the range knife here. This knife here is quite thick on the back. That is for strength. It tapers down toward the cutting edge. But when we get almost to the cutting edge, the taper changes from like this to about like this on the two sides. And that is to protect that cutting edge. If we sharpen this knife with the same angle all the way back to here, it would be so thin that it would hardly be functional right on the cutting edge. Let's think about another situation, and that is of the cold chisel. The knife that we just looked at is much harder steel and much sharper than a cold chisel. A cold chisel can very readily, with a stroke of a hammer, can very readily cut a nail with no problem at all. The question is, can this pocket knife do the same thing? Well, if you would take this pocket knife, get on the side of a nail, you'll find that yes, that knife will cut that mild steel nail. It certainly will. You can cut shavings as if you were sharpening a pencil with a pocket knife, if it's sharp. But after a cut or two, that edge is gone, and you will not be able to cut the nail in two. So what happens in the case of the cold chisel? We have a heavy, blunt, strong cutting edge. And consequently, with greater force, we can affect the cut. With the pocket knife, we have a more delicate edge that we can make very delicate cuts with, but it does not have the brute force and endurance that's required, for instance, to cut the nail. Now let's talk about what does the lathe tool bit look like. In the camera here, I can't very well demonstrate what these things look like. So let's pick a little example here. This is a tool bit, or an example of a tool bit made of a piece of wood. I stepped out to the shop and run these strips off on a circle saw and ground them to shape to not with a grinder, but with a disc sander. I sharpened these on a disc sander to be an example of what you would have in the small engine lathe, so that we may see this. And what we use in the watchmaker's lathe, clockmaker's lathe, is the same thing, just scaled down. So we'll be able to see the examples here. I touched the breaks of the edges around here with a dark colored pen so that we can see the shape a little more. So let's discuss first. I looked in a lathe handbook some time back, and I found a statement in a lathe operations handbook that just astounded me. It said that the lathe requires 5 basic tool bits. The lathe requires 5 basic tool bits. And I thought of that right quick, and I says, that's no way possible. No way possible. If they'd have said 500, I would have questioned it even less. But he went on to state that in your commonly used tools, there are 5 forms, and that all tools beyond those are simply variations of those 5 basic forms. And that is a very true situation. So let's discuss these forms. The first form is what's called a general purpose round nose tool. Now, This piece of wood that represents the tool is about 3/8 of an inch square, and it's about 2 3/4 inches long, something like that, and is not too different from the 2-bit that would be used in a small engine lathe. Small engine lathe being something up to, possibly 8 or 10 or 12 inch swing lathe. Let's see what the real McCoy looks like. Here's a 3/8 inch square, high-speed 2-bit as used in the engine lathe. This is just the way you buy the 2-bit. It's a blank 2-bit. It looks a little bit tarnished. I don't know. I've had this one in the clock shop probably 20 or so years. I brought it in from the machine shop to use as a spacer under something that I was doing, and it turned out to be such a handy tool I've never carried it back to the shop. Now, that 2-bit would cost about $4 or $5 in today's market. If you buy that 2-bit form ground, it will at least double its cost. That is, to get this 2-bit right here to this shape will double its cost. You'll find that you use a few general utility 2-bits, but for the most part the bit is ground to the job that is being done, and you will have dozens of 2-bits, and you will have to grind these 2-bits every few minutes. Most production machining operations or semi-large quantity production machining operations will have a pedestal grinder standing right beside the lathe. The operator starts a cut that's fairly long. He grinds several 2-bits while he's making the cut. He changes the 2-bit and he grinds them again right on the spot. Doesn't move from his workstation to grind his 2-bits. The alternative to that is to send them and have them ground by the tool room and have stacks of them, maybe even hundreds of them. Again, the economics of the situation is to grind it on this end, grind it on this end. Many like to grind 2 different bits, that is, 2 forms, different form on each end. Others like the same form on each end. You're making a cut, it becomes dull, you just flip your 2 posts around and keep going. Now, here's the bit, and let's discuss this. This is called the general purpose round nose bit. This has a kind of a spoon-shaped end out here. It is ground inward right here. The angle of that tip is like this. Here is the stock. Here is the angle of the tip. There are some very practical reasons for setting that angle at a pure value for certain circumstances, but generally speaking, an angle of about 10 degrees off of the top of the bit will be correct if the bit is held in a tool holder that goes straight into the work. You may have a tool holder that the bit sits at about a 7 to 10 degree incline, and the top of the bit may be straight. I prefer the tool holders that hold the bit straight in, grind the angle in the top. The second thing, here is the side of the bit, right here. Let's look at the angle here and here. This bit diminishes in width on the lower side. This angle again needs to be, just in general terms, about 10 degrees. Notice the end of the bit straight across would be about here. Again, this angle is about 10 degrees. This is a radius around here. This is a smooth radius. That can be ground in just a few moments on a bench grinder with a pedestal grinder with a rest to set the bit on it. Let's see how we use this. Here's a piece of stock that's a drop-off from the out in the shop. This is about a 2 1/4 inch piece of cold roll bar stock. It may be older than I am. I noticed that it's rusted pretty deep, but in the shop I was making something where that this was the end that was cut off, drop off. We can see the cuts here where the big power saw cut that off. We have a big power saw out there, and about the blade is fresh. In about 2 minutes we can go through a piece of steel this size. I have painted on this with a lacquer pen a black dot that represents approximately the center. This tool bit is a general purpose roughing tool. If we were doing a facing operation, which means that we want to face this true smooth on here, we could use this bit. This is not the best choice for the facing operation, but if we are in the lathe, the workman on this side of the lathe, this would be the right hand, this is the headstock end. You would set this bit at center level here, going straight in on center, and make the cut pulling out. Make the cut pulling out. Not on the point. The point is the most delicate part. That point is the most delicate part of the tool bit, and I could burn the point off of that bit before I could face this. But I go on to the side where that I'm using a broader surface and come out. Now let's look underneath and see what we have here. Notice that we have find the way. Notice we have cutting angle relief. See, this taper under here is a cutting angle relief, so that we're only attacking the material right on the cutting edge. Cutting angle relief. So we must have cutting angle relief on the back side. If we are scrubbing there, that consumes power. It does not increase the cut. It burns the cutting edge of the bit very quickly. We would normally drive this about something like 500 RPM, a piece of stock like this, squirt some oil on it, and we would pass out of this thing about this fast, making a cut about 0.010 of an inch deep. That's mild steel and a small engine lathe. Let's look at the general utility of this in turning here. If we were going to turn this surface, we could go in on the point, but remember, the point is delicate, easily burned off. Second thing, this iron oxide, this rough scale there, will eat the tip of that bit up before you know what happened. Making that first cut, we need to get underneath the scale as much as possible. Start in the edge, get underneath the scale, and pass under it with a slow first cut until we are cleaned up. So this is one of the big 5 tool bits. That's the round nose, general purpose tool. Round nose, general purpose tool. Now, if we were going to use a bit like this, I'm away in the picture here, if we were going to use a bit like this in the clockmaking work, would we grind it like that? And the answer says probably no. Probably no. We understand the cut. We understand that we have to have relief. We must have relief back here. See if we can turn this bottom up. And look, we've got relief here. This is called relief. We are ground down here, and the chips that come off of this come down here and must be turned up rather sharply. That function is a chip breaker. That breaks up the chip. If the particular material is more tenacious and the chip doesn't break readily, then this notch should be brought up closer so that it is bent, the chip is curved sharper and break it more readily. So you grind the chip breaker to get away from the nuisance of this type of thing. Question, do we grind this bit like this one? The answer is probably no. This being a handheld tool, we have the ability to roll it on the tool rest, on the T-rest. We can roll that tool. Let's look at one that I use here. Ground somewhat like this, not completely symmetrical. The left side of it is a little broader than the right side. And if I approach the work at an angle like this, let's see if I can, if I approach the work at an angle like this with a handheld tool, then I have effected the same as this relief here. This is called rake. That's called rake. The angle below the horizontal is called the rake of the tool. So by simply the angle that I hold the handheld tool, I can effect the rake and not grind that. Then what must I do to grind that bit to get in this tool the equivalency of this? Now that we understand how this one works, how do I do that? Let's imagine that this is a piece of tool stock. Let's imagine that's the end of this so that we can see what's happening. And let's imagine that this is the grinding stone. Grinding stone would be much larger than this. And let's imagine that we rest this tool on a tool rest that's at this angle to the stone. Tool rest is pulled up close. I grind this by sliding it on the tool rest, doing this. If we turn this way, possibly we can see this. I take the tool and I approach the stone like this, sliding it around the rest, back and forth, back and forth. And in not many strokes, I have effected this end right here. I ground this bit out on a little about 8-inch sanding disc. I just tipped the angle of the disc down, and it didn't take probably less than 30 seconds to do that. It takes a little longer in the real tool bit, but now that's how you produce this radiused end. So we would have here affected a tool bit. We grind a tool bit, the general utility turning bit. We grind one of these. It would look like this. Now, I know all the things that the Watchmakers Lathe literature and books and whatnot talk about on holding tool bits. They tell you to take the square tool bit, grind it on the end so that it presents a lozenge shape, diamond shaped on the end. They tell you to place this on the T-rest and attack the work at an angle about like this. I understand that completely. I also understand using the bow lathe, the English turns, and most of those cuttings are by scraping action, and they're removing very, very small quantities of material. That edge is very delicate. If you're really in the business of making parts where large quantities of material must be removed, that does not work. I grind the substitute for this type of tool. I grind the exactly like this, except the top of it is untouched up here. And then I get my rake angle by tipping it back. Now what does this do? That gives me a flat surface under here to rest on the T-rest. This situation of resting that on the sharp edge on the T-rest of your lathe dings up the T-rest, presents problems in that you can't slide it across the T-rest and whatnot, and you simply do better to have a group of tools and grind them to a more specialized shape. Substitute for this again would be the rounded nose and relief on each side. You can tip this tool to increase or decrease the relief. You can work it on this axis to increase or decrease the clearance below and the rake on the top. The machine tool industry, after whatever the machine tool industry has existed, has come up with a statement that the angle of the tool bit, let's look at this angle from here to here, that the angle of the tool bit for the best life expectancy and the best machining operation needs to be between about 60 degrees and about 80 degrees. Something between about 60 degrees and 80 degrees. That is the origin of this angle on the end of this piece of tool stock. That piece of tool stock is 60 or 70 degrees, 60 degrees approximately, right here. And when the workman grinds this, he simply puts it on the rest, on the tool rest, and rounds the edge, points the tip or whatever it is, and he can get to position with a very, very little bit of effort. If we look at the method that most of our watchmakers' gravers are ground, we find that the angle of this cutting edge may be 20 degrees. This one appears to be about 30 degrees. That cutting edge is very fragile. It will do delicate work, but if you must remove considerable material, that is too thin in the point. So much for the round nose tool. One of the next tools that we talk about is a facing tool. The round nose tool can be used in a facing operation and a turning operation. But let's talk about something that is used more nearly for turning. This is called a right-hand turning tool. right-hand turning tool. And it's a little difficult to get the key to memory on what is a right-hand tool and what is a left-hand tool. Let's look at this one. This one's a little larger. This is a left-hand tool. Let me put it in the left hand. This is a left-hand tool. This is a right-hand tool. What do we see there? You see their characteristic difference, other than a little in size, is this angle right in here. One is opposite the other. The right-hand turning tool, the function of that tool is to machine on the right-hand end of work. If this is stock that's being machined, this long angle here, right there, that angle is to work on the right-hand end of the material that's in the lathe. The left-hand turning tool works on the left-hand end of the stock. That's the difference. Let's see what this right-hand tool is good for. The right-hand tool is good for facing, like this. Start in the center, pull out. We've got the broad cut. We have the broad cut on the surface. We have the rake that we spoke of earlier. We have the chip breaker on the rake. Chip breaker may be pulled up closer depending on what the material is. We have the relief. This angle tips back down here that we have the relief from the cutting surface. And we have a small amount of utility on the other edge of it. The long edge is your primary cutting edge. You would machine like this. If you were taking a cut, you would you might well approach this work like this, traveling this way. That gives us a slicing action. That gives us a slicing action in the cutting. It makes it cut much, much easier with a less degree of heat. In grinding this tool, a variation of this is one in which this angle here, not only is it ground back this way, but would be ground down this way, being a compound angle. That would roll the chip off to the right. Many times it's important to see where we're working and the chips are in the way. So you grind the angle of the tool to roll the chip out of your line of vision. You can have a chip breaker, and you can have a right-hand roll, a left-hand roll. You can kind of roll the thing up and over the back, roll the chip whichever way you please by changing this top angle. This is to work on the left-hand end of the stock. You may ask me, well, feller, how can you work on the left-hand end if something's held in a lathe chuck? Well, you can't. You can't if this is held into the lathe chuck here. We can't work on the left-hand end of it. But remember this, a very high percentage of your most precision work is carried on centers. It's carried on a center. It's carried with some form of internal expanding mandrel, something where that the left-hand end of the work is accessible. It may be held, for instance, let's look at this micrometer barrel. If this were being machined, it might be held in a chuck by this tip here. We might machine the left end down this, out here, down this way, form these threads, and the last operation, when this is finished, we cut that tang off. So there is very much a place to work on the left end of material, very much a place to work on the right end of it, even on long bar stock. So We have a right-hand turning tool, left-hand turning tool, the round nose general purpose tool. That's 3 of the so-called Big 5. Let's look at this one. That's the most primitive tool, and it's for the roughest work. For instance, if we were going to get under the scale on this in the first pass, we would come into the side of this, somewhere along here, and we'd get under that scale and turn this, coming back this direction, with the tool on the line of centers. We turn back this way. I use tools like this in the tool slide of the watchmaker's lathe very, very frequently. Ground exactly like this, much smaller, of course, because notice this. I'm working on the right end. I'm working from the right side to the left side. So I'm working here. Turn this tool in the holder a quarter turn, and it'll work back the other direction. So you can grind this symmetrically, and you're cutting on this edge. Keep your edge something like this so that you're making a slicing operation. Holds the edge longer. Still another thing, carry a small stone, and a small stone may be about like this with the larger lathe work, but in the watchmaking, clockmaking business, you need a stone about 1/4 this big. And along the way, if that becomes dull, you just take this stone and you stroke it a couple of times, even with the tool bit, right in the tool holder, and you don't lose your setup, and you continue to go. A pocket stone. Mostly a machinist wears an apron with a pencil pocket up in the bib of the apron. Usually carry a little stone in that. You might even carry a round stone like this with a little practice. You can sharpen also with a round stone. So this is the 4th of your Big 5 tools. Let's look at the 5th. The 5th is a threading tool. A threading tool. The same principles in grinding. We have the rake. We have the clearance. We have the clearance on the 2 sides, and this is ground to 60 degrees, ground to a 60-degree V shape. I'm sorry I don't have my thread gauge here, but when you grind, the thread gauge is a little tool about the size of your thumb. One end of it has a 60-degree point. The other end of it has a 60-degree V, and in the side of it you have a little 60-degree V. What you do is you're on the grinder and grinding this, you trial fit. You trial fit the little threading gauge to this, and you grind the angle of it so that it just slips into the 60-degree V groove, and the form of your tool is correct for threading. Now, if we were going to thread this, we would take the little tool and turn it horizontal, and it has the 60-degree groove in here. We would rest it against the work, and we would slip the tool into that V groove, and we would line it up perfectly in the V groove and then tighten it in the tool holder. That guarantees that we go into the thread symmetrically on the 2 sides. The grading tool is very delicate on the end. If I should attempt to face the steel block out here on the end of a threading tool like this. I probably wouldn't make 5 turns on this metal till I would have burned the end off of it. That tip is very delicate from a heat standpoint. See, how do we thread with it? We go in and we make a small cut in the thread. So we make a small cut like this, primarily cutting on the tip. The second pass we come in and we ride one side of that cut and go a little deeper. And another pass we ride the side of the cut and go a little deeper. And we affect that side riding on the cut by the angle that we feed it from the compound on the tool rest, and that affects the highest percentage of the threading cut off of either the right angle or the left angle, depending on which way that we turn on the tool compound. So here's your big 5 tools. Now, I noticed in a recent flyer that for a set of tool bits that are 3/16 inch square, that would be tools that's this size, that they offered 6 tools for about $48 pre-ground. Now here's the type of thing that you would get on that. You get a tool that looked like that, you get one that looked like this, you would get one that would look like this, and you get a round nose and a couple of more, and that's what you would have. How long do those tools last? I can assure you that you will rarely ever use one without having to resharpen it. And that's the reason I start off with tool blanks. It's pure economics. The tools are great. As a matter of fact, this tool right here was purchased as a form grind tool. This one was purchased as a form grind tool. So on. Now, let's discuss where do we go from the big 5 tools. Let's try this one. That is that tool. Was that tool. That is a boring tool. That's the most difficult tool to grind of all. That's not an easy tool to grind. It's not that there's anything difficult about the shape. It's the fact that high-speed tool steel on a grinder, this is lots of material that has to be removed here. Can you see what's removed off of this? See what's removed here? Then let's turn it up on top, or on the edge. See what's removed here, and see what is removed here. And you see this hook in. This is a boring tool, and it has the same form that we've discussed earlier as the round nose tool or whatnot. We find that this is the cutting tip. If you're not familiar with boring, here's a little wooden punch case or something. Let's assume that this is in the lathe and we're going to machine on the inside of this. This tool would go inside like this, making an internal cut right on that tip. Say, what if I need to go that deep? Well, if the hole is big enough, you go in something like this. Machining on the line of centers in this way. The tool has the rake. Now, the business part of the tool is out this way. The tool has the rake, it has the clearance, it has the clearance, and it has the clearance here that we've discussed in the other tools. The basic grinding function of the tool is like unto the others. And this is a boring tool. You say, where do I need to do that in clockmaking? You cut a wheel on a wheel engine. It is discreet for the bore of that wheel to be smaller than its finished bore. The wheel is caught on its true OD, on its outer diameter. It's caught on the true outer diameter by whatever means. I prefer the so-called box technique that's discussed in some previous tapes. And then we go into that hole and open it up. Now this is an index plate blank. Let's say that this had to be opened up, that it was a wheel. We would go inside with this boring tool, also called boring bar, and open up the ID of that. That is an important tool to you, and in addition to the Big Five, is really nothing different in the cutting process, except that this particular one is ground as if it would be a round nose general utility turning. If we were threading, if we were cutting internal threads, we'd want the tip of that tool to be a threading tool. So that brings us to 6 tools. Let's look at this one. I have these tools, and I really despise the things. They're good tools. Many people use them. I never have liked the tool. This is called a parting tool. It's called a parting tool. This is ground with clearance this way. It's ground with clearance this way. It's ground with clearance this way. It's ground with rake this way. And in addition to that, the tool is a little broader at the tip than it is back here. See, it fishtails out ever so slightly. The purpose of that is we have an object in the lathe that we're turning, and let's say that we're making whatever this end might be. Then we go in with this parting tool like this and cut it off. It's also called a cutoff tool. I think the proper name is parting tool, but it's also called a cutoff tool. And we carry this down smaller and smaller and smaller, and we cut it off. It's also discreet when we're working that to crank our feed back and forth ever so slightly, like this. Cut a little wider than is necessary. You say, well, why didn't we grind the tool wider? Remember, we want to make the slicing cut. And as we're oscillating the tool like this, we are helping clean the tip. This type of tool is notorious for the material galling onto its tip. Remember that that tool feeding straight in is like the ranch knife trying to cut without slicing action. It would be like trying to slice a loaf of bread without cutting straight down without a slicing operation. That's the reason I don't particularly like the tool. I use them from time to time, but I really prefer to make my cutoff by some other means. I have power saws here. What I usually do is out in the shop out back, I have a big power saw there. I just whip the stock out of the lathe, put it in the power saw it off, put the piece back in, and then face it. I use the parting tool some, but it's not one of my favorites. Let's try another general purpose tool. This is a left hand. Okay, this is a right-hand general purpose. I'm sorry, I had it correct the first time. Left-hand general purpose tool. This is the right-hand tool. To look at these to see what we have here. This tool looks much as our round nose turning tool. It's a great similarity between the two. This one is rounder in the nose and whatever shape you want put on that. This one has a smaller radius. Ground the same way. This has some rake. It has clearance. It has clearance. And it has clearance. But let's notice the top of it. It has the chip breaker. But let's notice the top of this is at, here's the angle straight up. Here's the angle of the tool, top of the tool. This is made to work on the left side, left end, left face, like this. If I were facing this, this would be an ideal tool. I would face right out, like this, giving a slicing cut, rolling the chip to the side. Cuts very, very good. Come out to the surface, and with the round end, then I could pick up this surface, limited amount of round end work. Suppose I would go back into this side. No way. The angle's wrong. Cut. See, this angle is much greater than 90 degrees. So you see, this has to be used on the left end only. On the left end only, like this. I'm sorry, I was holding it wrong. I have to work on the left end only. This tool is about the same thing to work on the right side. This one is not ground with this long cutting edge as we had on that one. This is these are good general purpose tools. Now let's get to the handheld tools. We're talking about, thus far, we have been speaking of cutting angles, cutting philosophies. And it's important, if you're going to do machine work quickly and accurately and easily, it's important that we understand those, because that's just the way it is. Let's look at pretty much a favorite tool here. It would be handheld. Let's call this a handheld tool. Get out a piece of wood. This is a round nose tool. Has the rake, has the clearance, has the clearance. Grinding a handheld graver for the watchmaker's lathe in this form gives you a very, very good utility tool, an excellent tool. And again, I would not grind the rake into it here. I would grind the clearance a little greater back here, and I would tip the tool up more at an angle. Let's see if we can get in here, set the tool up more at an angle like this. I can't do that with this tool. See, the heel of it is touching down instead of the point. Grind this back a little more. How do we use that? Let me show you the utility of this. We can face with it on this side. We can face with it on this side. We can change the rake angle on it by tipping it this way, if we have enough relief here, even with the top of it straight. If we decide that we want to use a little scraping action for improving a finish, we can tip it sidewise. So we can roll it onto its side and do that. You see, this general type of shape in a handheld tool is probably has the greatest utility of all of your handheld tools. Just simple, round-nosed tool with quite a bit of clearance, flat landing on the bottom. Let's compare this, which we normally see in the watchmaker's literature. If we rounded the end of that a little bit, we'd have exactly the same thing, but we're always riding on the sharp edge of this. I prefer to grind it with the smooth landing down. Obviously you see that I have the types that I was just speaking to. Here's the tool, here's the form that we classically see in the literature on watchmaker's lathes. That's the classic form. This is either a square or a lozenge stock ground to a very steep angle on the back side. We're taught to present that to the line of centers. See if I can get the light in this. The line of centers, something like this. We're taught to ride the side of it, or over here, ride the side, do our center locating with the tip, and to break the shoulders, to get the sharp shoulders in like this with it. This is extremely thin. Tool ground this way, the cutting edge is very delicate. The point is extremely delicate. The tool that I use quite often in the handheld tool is like this. What do we have here? That kind of looks like a variation of this, doesn't it? Except, notice this is ground here and here. There's a ridge right down the middle. That strengthens the tip area, strengthens this area, and I use this tool like this, approaching the work. For instance, on the edge, making a slicing cut, or around here, making a slicing cut, or a slicing cut this way, or a slicing cut this way. And in using that tool, I have the additional strength under here, the additional ability to carry the heat from the point. I have the flat surface landing on the bottom, flat surface landing on the bottom if I turn the other way. I have also the ability to rock this up on the edge, but I do not have the ability to work it very well on the back side there. I believe this to be probably second, with this and the handheld tool to be number one and the most useful, this to be number two as the second most useful, and then pick this up as number three. Why don't we have 5 or 7 or 10 or whatnot of these tools as we do with the machine tools? It's pure and simple. As we roll these tools, as we swing them in our hand, they serve additional functions. You see, I can make this tool do essentially the work of this one, and of this one, just by rocking it. So as we look at the tools, this is forms that we use. This is philosophies of sharpening and cutting. And it would do you well, to study the theory of the cutting operation, because a little thought in your cutting operation can take away a sizable percentage of your regrind time. Now let's take, for instance, how can we save regrind time on one? Let's assume that I have this in the lathe, headstock here, turning. And let's assume that I am, it looks like that this cut right there was made with a tool that looked just about like that. That just about fits that form. Suppose that I'm coming along here and I find the tool is showing a little dull. I just move around in the holder like this and continue to come on. I need to make another cut. I move around like this in the holder, and that becomes dull. And I turn a little more like this, and I turn a little more like this. So you see, by repositioning in the holder, you can extend the cutting life of the tool 2, 3, or 4 times between regrinds. We can do the same thing with this type of tool, depending on where we're riding the surface at any particular time. Stay off the point. Stay off the point. If there's one cardinal rule in in all machine tools, is to stay off that point. Keep the edge angle. Keep the tool angle. We said something like 60 to 80 degrees. Keep that angle just as great as we possibly can. Make the tool, if it's feasible, make the curve on the tool as long as you can, so that as you use it, you can keep using additional spaces. All right, let's bring that part of our discussion to a close, and let's talk about the material of the tool bit. Where do we get these things? What is the material that we will use? What is this and here and that? If you look for a specialty house to buy a tool, you'll buy a general utility tool. And if you buy everything they've got, when you get down to the machining operation, you'll find that you still probably need to regrind and make your own tool. Again, this is some of the 093 rod stock, bar stock that I mentioned. It's heat treated on the end. This is 1/8 inch high-speed tool stock, commercially purchased. This is a piece of drill rod, and it looks like that it was ground to a small boring bar, probably to go inside to open up a small wheel or something there. That is held in this holder right here. This holder is split and it's eccentric, so this can be rolled in the tool post to raise or lower the end here. Piece of drill rod can be purchased commercially. Drill rod is nothing more than the type of steel that drill bits are made for. It's moderately hard, but it can be filed and sawed. It can be ground easily. Make this up. When you're finished, heat it hot, right on the tip end, quench it right in the cutting area. Very easy to make. Looks like that's another piece of drill rod there. The next thing to do is look at this. You recognize this as a rat tail file. Now, when that file is worn out, your heart couldn't desire a better piece of tool stock than the handle of that file. We break a drill bit. We break a drill bit. We use the shank of it to make a tool. Let's just pick an example right here in some of these tools. I think I have an example in here. What is this? This is a deburring tool. Looks like this is about 70 degrees, 80 degrees, something like this, countersink angle. That's the butt end of a broken 1/4-inch drill bit. And this was turned to the angle. It was heated, cooled, turned to the angle, then was heated and quenched in the end, and then on the stone, 1/2 the section was ground away, and that makes a fine chamfering tool used like this. So you see there are all kinds of places that we can locate materials for tools. Look at this. This is from a 1/4-inch drill stock, same type of countersink, both ends of it. The file is a great piece of stock for a tool. A piece of drill rod is a great piece of stock. Let's ask the question, how can I tell if a piece of steel can be heat treated? How can I tell if it will make a tool bit and will it work? Now, I know better than to make a tool bit out of that. Watch the end of this. You see the end of that wobble? That's a little key that goes in a chuck that I have for Watchmaker's Lathe. That's cold rolled steel. Just a little pull on that and that bent. It's been bent and I turn it and pull it again. That is not heat treatable steel. You get so that you can look at a piece of steel, just touch it with a little piece of abrasive paper and look at it, and you can get a pretty good indication as to whether or not it's heat treatable or not. And this is difficult to describe, but let me tell you a method that you can tell a piece of steel that is reasonably certain to be heat treatable steel. First place is touch it to a grinder. Touch it to a grinder. Hit it pretty hard just on a little edge, on the corner of the grinding wheel, and look at the sparks. Look at the sparks that comes off. If the sparks that come off of that steel look like little teardrop red darts, red teardrop darts, forget it. You can't heat treat it. Now, if you're going to experience this, you need to know what those sparks look like if you've never looked at them. Take a large nail and stick that nail to the grinding wheel to a degree that it sparks, and look at the sparks and fix in your mind those little red darts. You cannot heat treat and harden a nail. It's low carbon steel. The second thing is to take a file, like this little file, or a big old file that looks something like this, and get on the tang down here on the end. Now remember, the tang of this file is soft. I can see where I can file the tang of that file with another file. The tang of that file is soft. Get on that wheel and knock the sparks off from that. Look at the sparks very, very carefully. You'll find that a spark leaves this material, runs off the material, the spark runs down here somewhere, and that spark bursts like a fireworks display. That spark will burst. And if you're grinding pretty hard and there's enough heat in it, these little darts that leaves the spark, leaves the burst, they get a little further out and they burst also. And you'll find that essentially every spark that comes off that wheel will burst. A few of the sparks will burst from the low carbon steel, but only a very, very small percentage. If those sparks burst, then you have a piece of high carbon steel that can be made into a tool bit, can be heat treated, and will be functionally okay. The test: compare the sparks from the tang of a file, compare the sparks from a nail. While you're at it, just to dispel one particular imagination that we all have, turn around and spark the hard end of the file. You'll find the sparks are identical from the hard end of the file to the soft end of the file. It doesn't tell you whether or not the material is already hard. It tells you that it is high carbon steel. So any little scrap of steel that you pick up, you can do so. The second thing, touching something with a file doesn't tell you whether it's heat treatable or not. For instance, this right here is as soft as a nail. I can touch that with a file. This is not heat treatable. Here's some material in a baby food jar. The remainder of the container is somewhere else that had come in. This is called Casenit. K-A-S-E-N-I-T. Casenit. It is a gray powder, ever so slightly granular powder. That is used to case harden mild steel, to case harden the mild steel. For instance, this low carbon rod, which I said we cannot heat treat and harden, you bring this up to a bright red temperature and you just dip it and roll it into that casenet. It will pick it up onto the surface. You can turn it back into the flame and you can flow that material on it, and you do this for a minute or so and stick it in some water. Take this off and polish it, and you will find that it will be as hard as a file. Your file will just skid over it. But that's case hardening. The case surface may be only 1 or 2 or 3 thousandths of an inch deep. You cannot do that successfully on tool steel. So that's a method of identifying steels that are called high carbon steels, heat treatable steels, just in general terms, steels that are called drill rod, are all heat treatable and suitable for making tool bits. Remember, the prime requisite is that it must be harder than the material that's being cut, and that's pretty easy to achieve if you're cutting brass or mild steel. And the second thing is it must be very, very sharp. Very, very sharp. And buying a carbide tool bit or buying preformed, pre-ground tool bits does not obviate the requirement of sharpening tools. Sharpening tools is like paying taxes. It just never ends. Thank you. This is J.M. Huckabee. I am a certified master clockmaker, certified by the American Watch. Continuing on with the discussion of edge tools in the lathe, we have here the classic watchmaker's lathe. This is a Mosley number 2. I have a piece of 1/8 inch diameter stock in the spindle, the tip over T-rest. Let's turn an imaginary pivot on this stock with TwoBit of the type that we looked at earlier, and the tip of that TwoBit is ground something like this, the classic graver for the watchmaker's lathe, or approximately like this, which is the alternative grind that I was showing, but in reality it is like this with a much lower angle of taper. Now I will present this to the work not in the form that we usually see in watchmaker's lathes text, which is in this angle, but at the angle like this and like this. I'm going to cut on that edge, cutting downward, and we will form an imaginary pivot on the end of that stock and go through the things that you would normally do. The first thing that we do is form the center, which is nothing but point. This has an included angle of about 80 degrees there. It's purely to locate the center of rotation. And I'll go in here and start sliding the tool on the flat lower surface. That is, on the flat surface here that slides quite well on the T-rest. And I'll make strokes like this. And we'll just set some imaginary length for that pivot. We're sending these strokes outward, looking for it being parallel. With a little bit of practice, you can produce a remarkably parallel pivot with a handheld tool. And also, you can set quite a high finish on it. We'll estimate the speed that this lathe is running here in a few moments. Now, right here, I break the edge on this pivot to reduce the area that will catch the end thrust. We've reduced that somewhat, and I want to go in at this point and be sure that I have the no radius on that shoulder. No radius on the shoulder of the pivot. And we may want to come back and touch our center at that point. Now let's turn the motor off and take a look at this. Now I'll estimate the speed that we're going. My motor runs about 3,400 RPM. It looks like that my countershaft runs about half of that, which would be about 1,700. And the spindle runs maybe 10% faster than that. So I'm running close to 2,000 RPM at that point. Now let's see if we can look at this pivot, possibly with a magnifying glass here. I don't know if we can dodge all the reflections, and I can see the overhead fluorescent light here and some other things in this magnifying glass. Here is the tip end of the pivot and the shoulder, but not too well there. Let's slip this out and look at it with an eye loop. Let's see if I can rest this on my finger and get an eye loop. Look down in the eye loop and you can see this pivot. It's not real distinct. See if I can get in the center. See the pivot that we turned on this piece of stock there in the lathe. So that's how easy it is to form an imaginary pivot. We would use a target value on one of these and measure it with a micrometer or a vernier caliper or whatnot if we were making the real thing. That's how easy that the turning is. Now let's look at some rapid removal of material here. Get my safety glasses again. And this tool bit that I have here is ground much like the threading tool bit that we looked at earlier. The angle on the end is really about 90 degrees with some relief back on both sides. This is a pretty good rough cutting bit. I'm going to cut off this overhang that's on the stock right here, and we drop that off. Now let's see about how fast that we can remove material there if we so like. I got up to a kind of a scraping angle then, but we can see that the material can be removed at a very remarkable rate, even in watchmaker's lathe. This again looks somewhat like a pivot. I don't have the square shoulders on it. Let's see if we can get that in view. I'm having to look on the TV camera and try to find this in the high loop, so we see the turning at that point. So that's how easy it is to use the handheld tools. Again, I was presenting the tool at about this angle. This is about 10 degrees down from the line of centers. That gives me the top rake on the top of the tool. I'm ground back here to get the clearance underneath. Before the tape is over, I want to deal a little bit with sharpening the handheld tools. I want to pause here and set up the slide rest on the lathe, and we'll do a similar turning with the slide rest. We'll be back shortly. Returning, let's look at the tool holder that I'm using here. This is the tool holder. This is an eccentric really not the word, a swash plate type of washer, thicker on one edge than another for adjusting tool height. And this ring is a tool post or a tool bit raising ring. The slide rest that I'm using here, I use on several different lathes that have ever so slightly difference in the spindle height. In this particular lathe, I have to use the raising ring, and one of the other lathes I use a lesser ring, and in another I use even a deeper one. We have the two rings, and the tool bit that we're using looks similar to the general use turning tool. That is the first one that we looked at of the Big Five group. Has a slightly round nose, relief on clearance on the two sides and on the front. We'll sit this in here so that it almost comes to an almost parallel, the cutting edge almost parallel to the surface, so that we're cutting primarily on the side. We adjust the swash plate ring to set the tool on spindle center height. We tighten up the tool bit, and trying to get this behind here. Let me back the tool out so that we can see the spindle. The post itself is in the line of the camera, but we'll start the lathe and make a cut and show how easy that this is. Remember, the stock is 1/8 of an inch in diameter, and let's make a pass down this. Now, the pass that we've made down this looks like that it might be suitable size for, slide this back out of the way, for a large pivot in, for instance, an American clock. I'll get a caliper and we'll measure it and see how much we removed in that cut. The basic stock is 125 thousandths of an inch in diameter, which is 1/8 of an inch, and we are setting at 70 thousandths. So 70 from 125 is 55 thousandths of an inch. So the cut that we made was half of that in depth. 27 or 28 thousandths of an inch was the depth of the cut that we were making in that particular pass. This material is free machining. And if we ask the question, what is free machining? Free machining is a term that's about like what is expensive and what is inexpensive. Well, the term inexpensive really doesn't mean anything unless we have the reference that we're comparing it to. Free machining simply means that it machines easily, readily, or machines well. Machining well to a nice finish, but not necessarily easy, could also be free machining. Anyway, we would say that this machines very, very nicely. Let's make another pass here and see what else that we can do. Need my safety glasses on again. And we're making another pass, and let's make about one more. And we'll back out. Now, what we've done here, I believe this is a total of 3 passes that we've made on this, and we're 52 thousandths of an inch. That says that we have taken off about, I believe, 73 thousandths of an inch in diameter that we've removed in 3 passes there. So we do find that that is very, very free machining. If this were a pivot and is going to be used as a pivot, I would place a slight chamfer on the end to locate center on it for future use in depthing or polishing or whatnot. And that should have been done first, because as this pivot size becomes smaller and smaller, it is weaker when it comes to cutting out here on the tip end. So we should always locate center first. The next thing that we would do is take a handheld tool with a very sharp point. See, I mentioned this has a slight rounded tool tip, and we would go in against this shoulder and we would clean out that radius. So this shows the ease with which we can do this type of turning. This is a very simple turning operation, and one of the easiest that there is to do. Let's see if we can get into the eye loop here and see what this what this looks like. Well, having a little trouble here. About there. About there, we can see this pivot that we have turned. That is about 52 thousandths of an inch in diameter. You may notice that I use thousandths of an inch very, very frequently. Also use the metric system. When I mentioned that we could easily turn a thousandth of an inch or turn to a thousandth of an inch, what does a thousandth of an inch look like in the metric system? 1 millimeter is about, round numbers, 40 thousandths of an inch, just a scant 40 thousandths of an inch. And a tenth of a millimeter would be a scant 4 thousandths of an inch. A hundredth of a millimeter, which most metric micrometers are calibrated in, 1/100th of a millimeter is 4 10,000ths of an inch. 4 10,000ths of an inch, or in hundredths of a millimeter, it would take about 2.4 of those units, 2.5 of those units, 2.5 hundredths of a millimeter, if I could use such a term, is equal to a thousandth of an inch. On the other hand, if we're using an English micrometer and we read the vernier scale on it to a tenth of a thousandth of an inch, a tenth of a thousandth of an inch in round numbers is 4/10 of 1/100th of a millimeter. This gives you some relative comparison to the values that we're speaking of. This particular lathe compound is calibrated in thousandths of an inch. The IME lathe that's sitting on the bench right next to it, to my right, is calibrated in hundredths of a millimeter. So as we look at these, no, I'm sorry, it's calibrated in tenths of a millimeter, tenths of a millimeter. So as we look at the tools that we have here, we use them interchangeably between the two systems. Incidentally, the collet that I'm using here is a number 31. Number 31 collet. That is 3.1 millimeters in diameter, and that is almost exactly the value for 1/8 of an inch, which is 125 thousandths. You can usually hold 1/8 inch stock either in a 31 or a 32 collet. 31 is about 4 10,000ths of an inch or 5 10,000ths of an inch tight, and the 32 is just a little more than that loose. So it depends on the tolerance on the particular piece that is being chucked. We'll close this part of our discussion here, and we will return with some pointers on sharpening a few of the tools that we have been discussing. Returning, let's look at the sharpening process. I keep my stone wrapped in a piece of paper to keep the trash off of it. You'll look at the stone. It contains the mud from the previous sharpening. I spray this with a little WD-40 or kerosene, trying to protect the camera eye there. Take the TwoBit that I'm going to sharpen this lower surface. This is the type bit that we find classically for the watchmaker's lathe. I locate that bit so that I can feel that I'm landed down on the flat. And I start off working all over this stone in ovals, in long ovals, in straight strokes and whatnot to keep the wear on the stone pretty consistent all over. I don't want to gouge grooves in it. I just go over and over the stone like this, and make the longer ovals and whatnot, trying to use the entire surface of the stone. pick it up and see if I am landing on the flat, and I am. And after a short period of time, I lay this on the flat here and stroke it like that and like this. And then we wipe that off and we make a test on it. Is it sharp? And you try that in your thumbnail, and if it'll catch your thumbnail with that sharp edge, that's all there is to it. If we do that again, it's as simple as doing this. Our tape is just about expired. I rough these out on a little grinding wheel on a bench grinder, and then finish these surfaces like this.